Today we'll be looking at use cases in CockroachDB, specifically user accounts and metadata, that is, storing user account information and any metadata that's associated with those users in CockroachDB. Typically, your users will interact with an application which is backed by a database. They'll perform various operations which get translated into operations against the database. You'll be storing information about your users that enables them to use your application. That information might be their username or email address, their personal information or PII, any subscriptions they might hold within your application, and links to any assets they've created within your application, for example, their profile picture. Your application needs to be resilient, and CockroachDB is highly resilient to multiple types of failure. Let's assume in this scenario that we're running CockroachDB across 3 availability zones within a single US region. If any of those availability zones go down, CockroachDB will remain online because it's still able to achieve quorum between the remaining nodes. When the availability zone comes back online, so does the CockroachDB node within that availability zone, and data is up-replicated back to that node from the other nodes. Just as CockroachDB is able to survive availability zone failures, it's also able to survive regional and cloud failures via the same mechanism. Let's now assume that instead of running across one region in the US, we're now running across 3 regions in the US. If any of those regions become unavailable for any reason, CockroachDB will remain online just as it did in the availability zone scenario. Let's zoom out further. In the very worst outage scenario, an entire cloud provider might become unavailable. Let's assume in this scenario we're running across AWS, Azure, and GCP, and for one reason or another, the entire AWS cloud would have become temporarily unavailable. In this scenario, the nodes running across Azure and GCP would keep the service available while AWS is down. Your application might support a global audience of users, so your application and database nodes need to be close to where they are to give each user a good experience of your application. You might need to pin their data close to them to satisfy regulatory requirements. New users and markets can be reached as your application and user base grows. Typically, users will interact with an application, which in turn will hit a database via a load balancer. In a globally distributed application, this will usually be a geographically aware load balancer, which routes application requests to the nearest database. Although your CockroachDB cluster may be distributed across continents, it's still a single cluster managed centrally from one place. Adding a region to a CockroachDB cluster doesn't require downtime. In the case of a global table, data will be replicated to the new region in just the same way that it's replicated to the existing regions, while in the case of regional by row tables, data will only be housed in the new region if it's required to be there. The database and tables you go live with on day 1 will likely evolve as your requirements change. In a traditional database, this would require downtime while schema changes are made. CockroachDB allows you to perform schema changes with 0 downtime, allowing you to do things like add, update and remove tables, columns and indexes. Even primary keys can be updated without downtime. These changes are business as usual events and can be performed in CockroachDB while your team members are available. What I'll be creating today is a globally distributed database and application. If you saw the episode on IoT and device management, this will look familiar to you, but it will be users talking to an application that will be backed by CockroachDB in this example. There will be a globally distributed load balancer, which points users to an application running in fly.io. That will in turn talk to a load balancer, behind which will be a CockroachDB database with regions across US East 1, EU Central 1, and AP Southeast 1. I'll spin up a CockroachDB serverless cluster running across those 3 regions, with EU Central 1 being the primary region. I'll create a user called Rob and generate a random password for that user. With the cluster and the password configured, I'll be able to generate a URL to serve as environment variable secrets for fly.io and also access the CockroachDB terminal without having to copy-paste any sensitive information. The application will be a simple API that will load a database connection string from the environment, and it will expose a register and login endpoint, allowing a new user to register with the service, to log into the service, and then to view profile information. I'll be using Argon2 as a hashing algorithm for the password. Given a user password, I'll generate salt for that password and then hash the password with the salt, storing both the salt and the resulting hash in the database. When it comes to logging in, I fetch the hashed password and the password salt from the user account table, and I compare them against the hashed result of the password that was used at login time. And finally, there's a fetch endpoint that will allow a logged in user to view their email address, the avatar that was generated for their account, this is user metadata, and the date on which they registered. I'll spin up CockroachDB now. I'll connect to the database using the cluster information that was generated. And then I'll create the database. I'll call it accounts. The primary region matches the region that I created as the primary region in Terraform. I'll enable superregions to pin data. As with the IoT and device management use case example, if a single region within a superregion were to fail, that superregion would be unavailable. So that's why you'd want at least 3 regions within each superregion. I'm happy with just 1 region per superregion for this demo. The US superregion will contain the US East 1 region. The EU superregion will contain EU Central 1. And the AP superregion will contain AP Southeast 1. I'll enable auto-rehoming such that if a user travels, their data travels with them, giving them a good user experience wherever they happen to be in the world at that time. I'll create a user account table that has an ID, an email address, a hashed password, and the salt that was used to generate that password. It's always advisable to hash passwords with a salt value. The salt value itself isn't secret, but it does serve to make the hash data much more secure. There'll be a registered on date, which will be equal to now, the time they entered the table, and it will be unique on email address. This table is regional by rote, so it will give users closest to that region low read and write latencies. And it will allow us to pin data for regulatory compliance. I'll then create a table called user profile. This will store the user's metadata in this example. In this case, there's an account ID, which references the user's primary ID, and then a collection of bytes, which is the stored avatar for that user. Because this is a large column, I separate it into its own column family, just to make sure that whenever I make an update to the table that doesn't include this column, it doesn't try to update that column as well. This table's locality is global. There's nothing sensitive about this data, and it might be that users in other regions want low read latency to this data. They want to see all user avatars, for example. Next, I'll create the application. I'll call it CRDB user accounts. I'll make the database URL available as a secret. That will be passed as an environment variable to the applications. And then I'll deploy the application. This will be packaged as a Docker container, and I'll deploy a single instance of the application. Once that's successful, I'll scale that out to 3 regions to cover London, the US, and Singapore. With that up and running, I'll show that there's nothing currently in the user accounts table. And then I'll launch the front end, which is a simple Svelte app, and open up the browser. I'll register a new user. And with that user registered, I can now query the user account table, and we'll see that their ID, email address, password hash, and password salt have all been added to the table as expected. I'll now use that data to log into the application. And there's my very fetching profile picture along with my email address and the date on which I registered. That profile image is arriving as a stream of bytes that forms the source of an image tag. So in just 30 seconds, we've deployed a globally distributed CockroachDB cluster, and we can use it to safely store user account data and user metadata for users across the world with low read and write latencies for all of them. I've only really scratched the surface of what the user accounts use case is all about. I'm storing sensitive information and metadata, but it might be that users have subscriptions for various services within the application. All of these can be stored in CockroachDB, and depending on the table topology patterns that you use for that data, you can give users wherever they are a great experience of your application.